Good afternoon, ladies and gentlemen. Welcome to the first IEA GHG webinar of 2017, and I say Happy New Year to all of you. We see we've still got a few attendees joining, so I'll carry on slowly for a minute. As you know, we started this series about 2 years ago. It is proven to be a very popular series. We tend to present the results of the research work that we undertake, but in this case we are presenting, or we're dealing with a study which was a joint activity between which we were partnered to work done by VTT. So you will hear from Petteri Kangas and Christian Onnerheim on the study that we undertook in this area on the pulp and paper industry. I'm not going to elaborate a great deal about us, but if those of you not familiar with us, please go to our website at www.ieaghg.org if you need to know more about us, or contact us directly. To put everything in context, I think the Paris Agreement changed the world, I think, as far as we know it. Prior to Paris, the IPCC report, the Fifth Assessment Report, identified CCS as a key technology if we were going to reach a 2°C temperature target. Paris though set us the objective of going below 2 degrees centigrade with a target aim of about 1.5 degrees centigrade of global warming. And that means we have to do a lot more work to mitigate emissions, and that is not just from power sector, it's also got to come from industry, it's got to come in the transport sectors and also in agricultural. That's a bigger target to tackle. A lot of the work we've done has already shown that CCS is important in mitigating emissions in the power sector, but I think more increasingly we're seeing that CCS for industry, and particularly the heavy industry, is probably the only technology that can really mitigate CO2 emissions significantly in that area. And so this work is very important to us. We've undertaken a number of case studies going back over the years. We started working on the cement sector in 2008. We did a very detailed techno-economic assessment on an integrated steel mill in 2013. This latest in the series of pulp and paper will be followed quite quickly by productions on hydrogen production and methanol urea manufacture. We have a hydrogen refining study going away, and an LNG production effort underway as well. So this year will be sort of like the accumulation of all our work on industrial CCS, and then we propose to do a sort of covering summary of everything that's happened in this area at the end of it, particularly to aim to advise policymakers. I think one key learning, and my colleague Stanley Santos will always advise this, CCS in an industry is very site specific. So where we do a detailed study on a specific area, you can't really generalize that into conclusions on how CCS and costs might occur across the whole sector. And it's probably far more specific, site-specific, than the power sector. But nevertheless, each study is very opportunistic in its own right and delivers a set of information that helps us build the bigger picture for industry-based CCS and the costs associated with it. So at that point, I'm very pleased to hand over to Petteri Kangas and Christian Onnerheim, both from VTT, who managed the study that we were jointly active with. So I'll leave them to you now to explain the overview and the details of this study, very important study.
Thank you, John, for the introduction, and good afternoon, everybody. We are presenting today the results of assessing the retrofit of post-combustion CO2 capture in the pulp and paper industry. And I'd like to acknowledge my co-authors in this work, Stanley Santos from the IEA Greenhouse Gas R&D program, and my colleague here today, Petteri Kangas from VTT, and Ville Hankalin from OF Consult in Finland. And this work was undertaken as a cooperation between the Finnish National CCS program and the IEA Greenhouse Gas R&D program. So in order to limit the global temperature increase to 2 degrees Celsius or even lower as laid out in the Paris Agreement, the IPCC calls for solutions that can allow for negative emissions and actually remove CO2 from the atmosphere. And removing CO2 from the atmosphere could be possible by capturing and permanently storing CO2 generated during conversion of biomass. And an important prerequisite for assuming carbon negativity is sustainably sourced raw material, because if raw material is not sustainable, there is actually a risk that we don't only miss out on any carbon negative potential, but in the worst case, we can even go carbon positive. The pulp and paper industry is the largest industrial user of biomass raw material and has been identified by the IEA as a potential industry sector for large-scale CCS. And between 75 to 100% of the CO2 emissions from a modern pulp and paper mill are of biogenic origin. And this means that the industry has the potential not only to demonstrate CCS, but also bio-CCS. So, I would like to hand over the presentation to my colleague Petteri Kangas, who will present the reference pulp mills evaluated in this study.
Okay, our reference pulp and board mill is located in Nordic countries such as Finland, Sweden, Norway, maybe Canada, Russia. And here is a picture of overall of pulp and paper integrate. In our study, we didn't include all of these for the study, but we had either a standalone pulp mill or integrated board mill. But typical units such as wood handling, chemical pulping, pulp drying, and then stock preparation and board machine and related chemical utilities plants are included in this reference mill. And what is typical for pulp and paper industry is the heavy use of biogenic material. So here we see carbon balance of a pulp mill, and as we see, roughly half of the incoming wood is converted to real products such as fiber, board, paper, or minor products such as tall oil. And then half of the incoming wood is utilized within the integrate for producing the heat and electricity needed for running the mill. And if we are looking the fossil-based material, we only have very small amount of those. Heavy fuel oil is in our case utilized in the lime kiln for producing or the running the kiln. And then some fresh lime is also used for the process. But in general, we have three different sources for CO2 emissions. The one I just talk about, the lime kiln is one. Then the second is multi-fuel boiler, where all the bark and wood residues are burned. And by far the largest source of CO2 is the recovery boiler, which is utilized for converting the black liquor to the energy and then recovering the cooking chemicals. And one particular thing for the pulp industry is the lime kiln. If you think about the cement industry, these rotary kilns are a large source of CO2 emissions. But in pulp industry, in fact, almost all CO2 is biogenic, because the CO2 is eventually coming from the wood. It is dissolved within the pulp digester. Then it's then the black liquor containing the lignin and part of the hemicellulose is combusted in recovery boiler, and the CO2 is converted to sodium carbonate. And then this sodium carbonate is again converted to sodium hydroxide, and the carbon dioxide is going with the calcium carbonate. And then the calcium carbonate is burnt in or calcinated in the lime kiln, and all this CO2, which is originally from wood, is released. So practically, the calcination reaction is CO2 is coming from the biogenic sources, and only the fossil fuel utilized for running the kiln is fossil-based. And if we are looking for the reference mill in general, we have this fiber line where the wood is coming in, it's delignified, then it's bleached for removing the brown color, and then finally dried in pulp dryer. And if we are talking about the standalone mill, then the pulp is sold outside. And the production in our reference mill is 800,000 of pulp annually. It's a little bit smaller than, for example, the new pulp mill which is currently built in Äänekoski in Finland. I think the capacity is something like 1.2 million tons annually. But otherwise this is representing typical pulp, modern pulp mill. And in that case we have quite a lot of excess heat and electricity available because the processes are efficient. And if we are looking for the recovery line, we have this evaporation where black liquor is evaporated, then it's combusted in recovery boiler, and then the lime kiln for recausticization and so on. And then the multi-fuel boiler is used for combusting the bark and other residues. And in second reference mill, we call it base case B. We have also the board machine included, and the major difference here is that board machine is of course utilizing some of the heat and electricity and also pulp, and in that case we do not have so many megajoules or gigajoules available for the CCS plant to be run, so less excess heat available in this second reference case. And if we go further, we see the rough material balance of this mill. So the wood utilized for producing 800,000 tons of pulp annually is we need 4.6 million cubic meters of Nordic pine and spruce altogether. And then we have some cooking chemicals, bleaching chemicals, sodium hydroxide is about 30,000 tons annually for that purpose. Quite a lot of cooling water, mainly for the running the turbine is needed, but luckily our mill is located by the coast or by the river, so that can be handled. And then electricity utilized in mill or produced in mill is 900 gigawatt hours per year for the standalone mill, and then for the integrate a little bit less, 130 gigawatt hours per year. And besides the electricity, the other important thing or side product from the pulp mill is crude tall oil. About 30,000 tons per year is produced. And if we look about CO2 emissions, the recovery boiler is by far the largest source. 1.6 million tons every year is the emissions, and then a multi-fuel boiler and lime kiln are in same level, about 0.2 or 0.3 each year. And if we look at this plant, we see that for the second case, we are utilizing high pressure and medium pressure steams are the same, about the same, but for the case where the board machine is included, we need more low pressure steam for running the board machine, and of course that is away from the to be utilized in CCS plant. And also the same phenomena can be seen for the electricity consumption. For the standalone pulp mill, it's 640 kilowatt hours per ton of pulp, but in base case B we have 990, when we are producing about 400,000 tons of board besides this pulp every year. And that will result less electricity export, and if we are utilizing heat, that will of course reduce the amount of electricity export, and if we consider this electricity as green electricity, that might be some side effect of this CCS plant to be installed. And when we are talking about utilizing this excess heat from the pulp mill, here we have defined that the CCS plant is utilizing mainly 2-bar steam, and we have 3 different options to take the steam or integrate CCS plant to the mill itself. So first is to utilize this low pressure steam. If that is, and then reduce it to 2-bar steam. If that is not enough, we can take a little bit higher medium pressure steam, 13-bar steam, and get slightly increase of amount of 2-bar steam by utilizing that. And the third option is install steam-driven CO2 compressors, and in that case we will have a little bit better process integration available. In cases that steam or heat is not enough steam or heat is not available, we have option for installing auxiliary boiler for producing the excess steam for plants. And when we are talking about the reference mill, so if you want to buy this kind of pulp mill for the standalone case, we are talking about 800 million euros investment, and for the integrate pulp and board mill it's 940 million euros. And largest parts, or the most expensive parts, are recovery boiler, and then pulp dryer, board mill, and then cooking plants. All of them are over 100 million in investment. And finally, when we are looking at this reference mill, what is the cost of pulp, levelized cost of production of pulp? We see that the value here is 523 euros per ton, and the largest factors here are raw materials, mainly wood, and then the capital expenditure, which is the second largest, but all the others are minor. And if we are looking for the electricity and the crude tall oil, we will here gain some benefits, because here we are considering the pulp as the main product, and these side products will result some lower value for the pulp price. And if we look for the board price, here 679 euros per ton is achieved, and also the raw materials here coming from the pulp mill, but also some purchased pulps are utilized, and that is the almost the only cost factor seen here. Of course, capital has something to do, and then we need some electricity for running the mill. So if we are utilizing the board mill or installing the board mill, we will have less excess in electricity available, and that will result some also for the integrate or the cost structure of whole integrate. But these are the base cases 1 and 2, the standalone mill and the integrated pulp and board mill. And then now Kristin will continue and tell about how the CCS plant is installed here, and what is the effect of those also for the cost structure.
Okay, so we evaluated 6 cases for each of the 2 reference mills, as described on the left-hand side of this slide. We looked at capture from the recovery boiler only, from the multi-fuel boiler only, and from the lime kiln only. And then we also looked at 3 combinations of these. And we assume 90% capture rate for all the cases. So all in all, 12 different cases of CCS integration. And as was mentioned previously, there is less excess steam available at the integrated pulp and board mill, and as a consequence, for a 90% capture rate in cases where we capture from the recovery boiler, there will not be enough excess steam on site. And as Petteri mentioned earlier, our solution was to add an auxiliary boiler for additional steam production, and also we switched the electrically driven CO2 compressors for steam-driven compressors. And these cases are marked with an asterisk in the left column. And CO2 capture from the additional auxiliary boiler was not evaluated. And if we look at the left-hand side of this table, we see that we have the total emissions from the site after capture implementation, and we also see how these are allocated between biogenic and fossil emissions. And when calculating cases including fossil emissions, in other words, capture from the lime kiln, we assume that 100% of the fossil emissions are captured first before any biogenic CO2 is captured. And on the right-hand side, we have the total capture and the direct CO2 avoided. If we look at the pulp mill, we see that total captured CO2 equals directly avoided CO2, since the CO2 capture implementation does not cause any additional emissions. And for the integrated board mill, on the other hand, the CO2 emissions from the auxiliary boiler have to be accounted for, and this lowers the overall capture rate and the directly avoided CO2 for the cases where we capture from the recovery boiler. And I'd like to underline this difference when we here estimate the negative emissions by pointing out two things. One is that this study assumes that biomass utilized as raw material is sourced sustainably. And the other thing is that we don't take into account any CO2 emissions that arise in the raw material subsidy chain outside the mill battery limit. So this means that in reality, taking into account impacts of bio-CCS such as land use change and so on, the potential for negative emissions will be smaller. This is a simplified illustration of the post-combustion CO2 capture unit, and this consists of a direct contact cooler, a CO2 absorber, the main heat exchanger, and a stripper with reboiler. And all flue gas is treated in electrostatic precipitators for dust and particulate removal. And flue gas is then going through the direct contact cooler to further reduce any particulate matter and to cool the flue gases down to 40 degrees Celsius. And the stripper reboiler is powered with steam from the steam turbine island. And we use a conventional 30% MEA solvent, and we also applied a split flow configuration option in order to reduce the heat duty of the reboiler. And the pre-treatment of flue gases in this study is minimal. The SO2 concentration in the flue gases, both from the recovery boiler and from the multi-fuel boiler, is typically very low. And for that reason, it was decided not to include a flue gas desulfurization plant. And instead, it is possible to add, for instance, sodium hydroxide in the direct contact cooler in cases where the heavy fuel oil used in the lime kiln has a high sulfur content. And because of this solution, we also assumed a slightly higher MEA makeup rate when calculating the operational costs. And the CO2 compression is not shown. We applied a 4-stage compressor train with a molecular sieve for dehydration, and the CO2 is compressed to 110 bar in the end, ready for transportation. So this is the steam balance of the reference mills with the retrofitted CO2 capture. As mentioned earlier, the main approach to integrate the CO2 capture plant steam requirement was to extract 4.2 bar low pressure steam from the steam turbine and then desuperheat this to 2 bar ultra low pressure steam. In the pulp mill, for all capture cases except capture from all 3 sources, there is sufficient 4.2 bar steam for 90% capture. When it comes to capturing CO2 from all 3 emission sources, this requires additional steam to be extracted from the 13 bar extraction point. For the integrated pulp and board mill, we already mentioned that cases including capture from the recovery boiler require additional steam. And the auxiliary boiler is sized according to this additional steam requirement. The auxiliary boiler delivers steam at 13 bar. And this steam is utilized in the CO2 compressors. And in turn, the CO2 compressors produce 2 bar ultra low pressure steam that is used in the reboiler. And any additional steam demand in the reboiler that cannot be met by the CO2 compressors has to be satisfied by extracting and desuperheating 4.2 bar steam from the steam turbine. This table shows the electricity balance for both retrofitted cases. And for the Kraft pulp mill, the additional electricity demand when integrating a CO2 capture and compression plant sums up to 3 to 30 megawatt, depending, of course, how much CO2 is captured. For the integrated pulp and board mill, because we use steam-driven CO2 compressors instead of electrically driven compressors, there is no longer need for all that electricity for CO2 compression, but there is slightly more electricity needed for running the auxiliary boiler. And the changes in the electricity balance after CO2 capture retrofit translate into a decrease in renewable electricity exported to the grid. And for the pulp mill, this sums up to a 20 to 50% reduction, and correspondingly for the integrated mill between 30 to almost 90% reduction. Now we made a discounted cash flow analysis to calculate the levelized cost of pulp after implementation of a CO2 capture process. And the cash flow analysis was made for 25 years of mill operation, and this table presents the results for the different capture configurations for both reference plants. And with CCS, the pulp cost for the Kraft pulp mill could reach as high as 680 euros per air-dried ton. And compared to the reference mill pulp price, this is an increase of almost 160 euros per air-dried ton, which is quite significant. For the integrated pulp and board mill, the levelized cost of pulp was calculated by fixing the board price of the reference case in order to be able to compare these two different mills. And also, since we feed in different kinds of imported pulp to the board mill, this method enables consistency in evaluating the market pulp price for the two different mills. And similarly, the cost of CO2 avoided was estimated, and the difference of 20 euros, around 20 euros per ton between the Kraft pulp mill and the integrated pulp and board mill is mainly due to the additional auxiliary boiler and the investment for the modifications that have to be done to the existing mill because of the CO2 retrofit. Here we see a breakdown of the levelized cost of pulp, and now we're looking at the pulp mill only. And the levelized cost of pulp is mainly affected by variable costs, especially maintenance, chemicals and utilities, and also capital costs. So the results of CO2 capture integration were assessed for 6 different policy framework scenarios to see how these affect the product price. And in scenario 1, we have no CO2 tax whatsoever, and because of this, it doesn't really matter whether the CO2 emissions are categorized as neutral or not. Then in scenario 2, we add a CO2 emission tax, and we also assume that biogenic emissions are not recognized as neutral, which means that in scenario 2, all CO2 emissions are taxed. In scenario 3, we still have the CO2 emission tax, but now the biogenic emissions are recognized as neutral, which is the current situation in the EU ETS. And in scenario 4, we add an incentive for renewable electricity, and the baseline price for electricity used is 40 euros per megawatt hour, because this is currently representative for Finland. Scenarios 5 and 6 take into account a possible incentive for negative emissions, and scenario 5 is the same as scenario 3 plus negative emission incentive, and scenario 6 is the same as scenario 4 plus negative emission incentive. Now this chart shows the effect of the electricity price on the break-even price of pulp. And the base case, or the reference mill, is shown as a dotted line, and again we're only looking at the Kraft pulp mill. We had a base number for the price of electricity at 40 euros per megawatt hour, and in this illustration now we clearly see that there are 3 major capture rate categories. We have the 2 green lines which represent the multi-fuel boiler and the lime kiln, that are low capture category with a capture rate of 5 to 15% of total site emissions. And then we have capture from the recovery boiler plus the multi-fuel boiler, and from the recovery boiler plus the lime kiln, which represent a medium capture rate of around 60 to 80% of total emissions. And then in the end we have the high capture rate, which is capture from all 3 sources, which has a capture rate of more than 80% of total emissions. And as we can see from the chart, the cost of pulp will, as expected, drop when the price of electricity increases. And this is because the revenue from renewable electricity export increases. And the drop is steeper for the low capture cases because in these cases the utilization of excess steam is lower, which results in more electricity generated for export. And for the medium and high capture cases, the energy requirement in the CO2 capture plant reduces more significantly the amount of electricity to the grid, and as a result, the effect of the electricity price is smaller. And similarly, we see the effect of the electricity price on the cost of CO2 avoided. And again, the red rectangle illustrates the baseline number, or scenario 1. And here we see the economies of scale illustrated with the low capture category cases, or the multi-fuel boiler and the lime kiln in the higher region, while the higher capture rate categories are concentrated at a significantly lower cost. And what we can conclude from this is that the price level of electricity affects quite significantly the cost of CO2 avoided. And again, we see that when the electricity price is low, the higher capture rate cases are most favorable. And this is because of the option to export renewable electricity to the grid. Now, these figures compare the two extreme cases when biogenic CO2 emissions are recognized as neutral and when they are not. So we are comparing scenarios 2 and 3. And on the left-hand side, the CO2 emissions are recognized as neutral, and due to the large share of biogenic emissions from the pulp mills, we don't expect any major impacts on the price of pulp, even when the CO2 tax increases quite significantly. And for comparison, on the right-hand side, we assume that biogenic emissions are not recognized as neutral, which means that all CO2 emissions are taxed, and now we can expect to see a significant effect on the levelized cost of pulp. And one thing to keep in mind here is that, for instance, in the EU ETS, the emissions from the lime kiln are considered 100% fossil, which means they are taxed as a total, even though, as Petteri explained earlier, more than half of the emissions originate from the recovery boiler. Now, this chart illustrates the effect of a possible negative CO2 emission credit on the break-even price of pulp. And again, we are looking at the market pulp mill only. And here we see that in order to cover the additional costs of implementing CO2 capture at the mill, the cases with high capture rates will of course benefit the most, while low capture rate cases will need a significantly higher negative emission rate in order to become feasible. And in order to reach a break-even price of pulp around the same level as for the reference case, the market pulp mill would need a negative emission credit of around 62 to 65 euros per ton CO2 for the high capture cases, and then from 90 and up to more than 100 euros per ton for the low capture rate cases. And the corresponding break-even prices for an integrated pulp and board mill are typically 10 euros per ton higher than for the market pulp mill. And again, as long as biogenic emissions are recognized as neutral, the CO2 tax will have little effect on this break-even price. And here we clearly see that for a negative emission credit above the break-even price, the pulp and paper industry would actually have the means to create business cases from a negative emission scheme. And this could allow the sector to actually create a new source of income with bio-CCS. For going to the concluding remarks, as mentioned in the beginning, the retrofit and integration of CCS, and especially for the pulp and paper industry, is very site-specific, but this study gives a reasonable baseline information. And in the case of a market pulp mill, there should be enough excess steam to capture 90% of total site emissions. But again, this is site-dependent because various mills may have different ways of integrating energy production on site. And regarding the integrated pulp and board mill, there is not enough excess steam for 90% capture rate, and additional energy will be needed. And with 75 to up to 100% biogenic CO2 emissions, there is a significant potential for the pulp and paper industry to demonstrate both CCS and bio-CCS. However, this is not currently attractive for the industry, as biogenic emissions are considered neutral in the EU ETS. And as we have shown in this study, the additional investment of CO2 capture will increase the product cost, and unless this is addressed by incentives, such as, for instance, negative emission credits, it will be the market who pays the additional cost. And as long as carbon reductions are not required from a global pulp and paper industry through, for instance, binding international agreements, this will cause a competitive disadvantage for the part of the industry where CCS one day might be required. On the other hand, if negative emissions would be accredited in the EU ETS, there would be a chance for the industry to create business cases, and the sector could even become a forerunner for industrial implementation of both bio-CCS and CCS. In order to make CCS attractive to the pulp and paper industry, a negative emission credit of around 60 to 75 euros per ton CO2 is needed, and this is quite far from the current 4 to 5 euros per ton in the EU ETS at the moment. So if you have any further questions that have not been addressed here today, then please feel free to contact us. And with that, I would like to thank you for your attention, and I'll give the word back to John.
Thank you, Petteri. Thank you, Kristen. I do apologise to those who asked the question. I was so keen to get this webinar underway and so excited about it that I forgot to give my name. My name is John Gale, General Manager here at the IEA Greenhouse Gas R&D Programme. Thank you both for an excellent presentation. Thank you all for staying with us so far. We have some questions, I believe. One of the questions we have is India needs funding for its CCS pilot projects on biomass for its pulp and paper industries. Do you know how you could get those sort of projects funded? Somebody suggested maybe the Clean Climate Fund. I'm probably thinking that isn't an adequate route to sort of suggest that. Maybe something like the CDM.
I have to admit that I'm not very.
Okay, what we'll do, I think, is we'll do a little bit of research and come back to the person concerned and come back to them. I have another one here. Always make life difficult. Question: the findings, would they differ for other geographical regions? And I think this comes back to the whole issue of site-specific specificity of some of these activities.
Yes, for instance, the CO2 transport and storage cost would be different. And as we have shown in the main study here, we use 10 euros per ton for CO2 transportation and storage. And for Finland, for instance, that would be a lot higher. That would be closer to 30 euros per ton, which is a direct addition to the cost of CO2 avoided.
One additional note related to the pulp and board mill is that in Nordic countries there is usually the excess heat is utilized. One place to use it is for heating the communities or nearby the processes. So in many cases it might be so that at least part of the potential is already used, at least during the winter time. But if you think about the southern part of the world where excess heat is already available and you don't need it for heating the plants or homes, there might be bigger possibilities for installing these technologies. Of course, the efficiencies of modern pulp mills are the same. It doesn't depend whether you install them in Finland or in southern hemisphere or somewhere between, but the utilization of excess energy is the key. How is there available and how much and will it be reduced by or something else?
That's an interesting question in itself, isn't it, Petteri, regarding in a sense in Nordic countries the heavy high demand on heating and use of waste heat, whereas in other regions they're not. But if you are using a substantial amount of the waste heat already for district heating, how much does that mean that you have a plant that you possibly, I think you linked on it, you probably only use the CCS option in the summer. Does that make it a worthwhile investment?
At least I think that could be a limiting factor. But coming back to my explanation is that I know that in Finland these modern modern plants, they now have excess amount of wood residues, and they don't really know how to utilize those because they don't need all the heat by the site. So I think that problem is not so big. The big pulp mill is producing a lot of heat, and towns nearby are not so big ones. So there could be possibilities also. But traditionally in Finland, this CHP has been heavily utilized where it has been available. But I don't know if that's the story in the future.
Yeah, on that same sort of topic, we've got a question here. How feasible is it to have CCS on CHP? I mean, it gets back to the fact, are they compatible? And I think you've probably answered that to a degree if there's extra excess pulp or wastewood available. I mean, a general question here is, can you quantify how much steam was required for regeneration of the amine and what the impact on the overall energy balance was?
As I explained, we used a split flow configuration in the CO2 capture plant. So we had a reboiler duty of 3.1 megajoules per kilo, which is compared to 3.6 megajoules per kilo.
Sorry.
I think with more tailored amines nowadays you can even go down to 2.5 megajoules.
Yeah. Okay, that was that. You just answered one of the questions that just came in. Which was, have you looked at the impact of improved solvents? And you just answered that one. Have you looked at the energy penalizing technologies? No, sorry, I'm struggling with. But we've got a question here. There is some technologies out there like CO2 solutions, enzyme capture systems. Did you look and consider whether those technologies might be suitable as in the capture process here?
Those technologies are known, but they were not in the scope of the study. So they would be really interesting. It would be really interesting to compare them to the study that we made. But none of those technologies were considered in this work.
Okay. We talked about steam regeneration. Question, a general sort of question is it? Do you think it's easier to capture CO2 from other sectors than the pulp and paper one, or does this present more so unique challenges?
There might be challenges concerning the size, for instance, because these plants may be more decentralized. The scale is maybe not so large. Another possible challenge might be particulate matter or dust in the flue gases from the biomass or other pollutants from the biomass, but otherwise I don't see any big challenges compared to other sources.
Okay. A sort of $1 million question here that's come in. What's the sort of interest in the pulp and paper industry regarding the application of CCS? What's their attitude to it?
Well, it's a challenging question because, for instance, in the EU, as I said already, in the EU ETS, biogenic emissions are not, they are recognized as neutral, so they are not taxed, which in itself doesn't make any incentive for the pulp and paper industry to be interested in CCS. There is, however, in Canada, there are initiatives on bio-CCU where they are planning to implement CCS on a pulp and paper mill and use the CO2 captured. So it's also a matter of policy and which part of the world we are talking about.
Okay, just wrap up. One quick question that's come through is, will the presentation be available afterwards? And that is definite. Yes, we make all of them available. And I think we're getting close to the end of time now. We'll take one last question here, and any other questions we get, we'll log them and respond directly afterwards. This is a sort of a generic question. You've looked at one type of technology, the Kraft pulp mill. I mean, it's a bit of a teasing question, this. I mean, it's asking to do some results before you've even done them, but are there other types of pulp mills that you think may be easier to capture CO2 from than the Kraft type process? Or do they all offer the same sort of challenges?
I think that Kraft pulp mill is currently the dominating technology. If you think about the volumes in global, of course there are sulfide pulping and then some sort of agro pulping technologies available. Then some new wood fractionation technologies might be emerging in the future, but currently it is dominating technology, and I think that the same results can be generalized in other sectors too. We have wood, and then we are utilizing half of it for energy production currently, and there are a possibility for using this heat for CCS, and that's a good opportunity.
Yeah, and it's common to other sectors as well. All right, well, I'd just like to close down now. I'd just like to thank Kristen and Petteri for a very interesting sort of presentation. And that's all from us for today.
Okay,
thank you.